So welcome to video 6 in our course on linear models. Now we're looking at confidence intervals and prediction intervals. So that's estimating the extent to which our particular model, like the fifth line here, how confident are we of the population mean for weight based on height, and to what extent can we predict estimates for new data that might have particular values of height to estimate their weight. So like a standard error, confidence intervals give a sense of where the population mean is. So CI stands for confidence interval, PI stands for prediction interval, and using this table, we can get a sense of what these kind of error bars can indicate. So you have things like the standard deviation, which is useful because it tells you about your data set and the variance of your data set. The standard error is perhaps less useful because it measures how um, uh, it gives you estimate of the sample mean you have for that particular data set. And the confidence interval is associated with if you repeated the study numerous times, that your estimate of the sample mean would reoccur within a 95% time in those particular interval of values. So a decent estimate of your 95% confidence interval is it's about twice the standard error. So if you're using standard error for your error bars, it's not very wise because it's really underplaying the extent to which there's variance in your data. So in general, for confidence intervals, we can say that if you repeat any experiment 100 times, the confidence interval of a particular percentage, such as 90%, will contain the population parameter X% of the time, so maybe 90% of the time. So that means 10% of the time, your sample mean will actually not be inside that confidence interval. And the individual values might have much wider variance from that. And that's where prediction intervals come in. So individual values may have much more variance than that you've assigned there. So another way of thinking of that is that to use an archery analogy borrowed from Ebi the target is fixed and the true value might end up in the interval. So think of them like this, where you're shooting at a board. However, it's like a ring toss. The true value is fixed and the interval might end up around it. So our interval is kind of the thing that is being placed on our value. And if our constant interval is about 90%, then we can that's the set of confidence that we can have that our ring toss will actually land on it. So if we have a bigger sample size, we'll more likely get the true population parameter. So if we want to predict weight based on a value for height, so let's say height 21, which you don't observe in this distribution, we have to consider the error for each data point. You can go to kind of get a sense of it there. We can do that by getting the sums of squares of errors, SSE, the residuals, based on our fit here compared to the original values. So that gives us more information. So effectively what we're seeing is we're getting the expected value for y, given that x is 21. And we consider, okay, what weight would that have? What's a kind of a confidence interval for getting that weight as well? So another graph for this problem is that if we consider we're looking at confidence intervals, if we think at our mean here, if we do lots of different experiments here, we'll tend to get variation within each experiment. And for 95% confidence interval, will mean that 19 out of 20 samples will contain the true population mean, but one of the 20 won't. Another illustration is here on the next slide, where we have a population mean of 40. You can see here in the dotted line, and we have sample means shown as the black dot, and the bars are 95% confidence intervals. So these have sample size of equal to n equals 10. So you can see that they vary considerably. And if we had a larger sample size, we find that the confidence intervals were smaller and would likely be more reliable. So what confidence intervals are telling us is about that the sample means are within a certain range of the population mean, and that's different from prediction intervals that refer to the data points themselves and their variance. So you can see the extent to which standard error, which just has this formula, varies across different populations as we increase the sample size. So here we can see a smaller sample size has a bigger standard error. And if we increase that sample size to 50, we have a smaller standard error. If we increase it again to 100, again, it decreases, and so on and so on and so on. That means graphically we can illustrate like that. If we have some sort of dependent variable here where the m indicates the mean of 40, the standard error is shown here as being the smallest value because it's divided by the sample size here. So you got n equals 3, we have a smaller standard error. Whereas if we increase n equals 10, it decreases further and further here. But you see the standard deviation here is constant across all three sample sizes because that affects the underlying data size. The confidence interval refers to our estimate of the true population mean in the context of our sample. And you see that decreases as we increase the sample size. That's where the standard deviation differ from the standard error in the confidence interval, and standard deviation is more linked to the prediction interval. So confidence intervals predict the population mean. That's related to the standard error. Whereas prediction intervals predict the next data point of being in a range that depends on the sample variance and the standard error. So actually the standard error plus the standard deviation. And this matters in the sense that if you're taking care of patients, you have to predict accurately for the next patient. Whereas if you're culturing bacteria or viruses or whatever it is, if depending on your experimental setup, if a lot of them die, it may not matter. So if we look at this graphically, we can look at the 95% confidence interval here for n equals 5 sample size. And we can get, if we repeat this many, many times, we'll get this kind of spread of values for the confidence interval. Whereas for prediction interval, we'll find that's much, much wider. So our data points may be right out here, right out here. This distribution here is of our sample means. And that's merged by our confidence interval. This is of our underlying data from which we can summarize to get our sample means. So you can see these overlaid. This is our confidence interval for n equals 20 and our prediction interval. And if we increase the sample size, you can see the older distribution is much, much wider. And this one is much, much narrower now. So our confidence in the true population mean is much, much narrower, but we still get a good spread of values, good spread in our values because that's their underlying features. There are formula then for getting our fitted estimate from a particular mean from a bunch of values in X, which is this formula. So it's a function of a t distribution by the mean squared error of 1 over n by the sum of squares of values of X for the different parameters that we're using divided by the sums of squares of X. That's the formula for using it, and we'll be able to use an R function to do that more efficiently for us. An example of where confidence intervals matter comes from the Oxford AstraZeneca vaccine placebo initial trials that were being run back in 2020. So these people were exposed to SARS-CoV-2, and some got the disease and some didn't. So if we see here, for those exposed to SARS-CoV-2, we have a ratio of 3 to 30 for those infected in the UK versus in the context of getting low and high doses. And the efficacy was shown to be about 90% from a sample size of about 2.7K. In Brazil, those who got infected for high and high doses were the sums of this number there, so at 98. And their efficacy of that trial in 8.9 thousand people was 62%. So the reported efficacies and the 95% confidence intervals were quite different here. So for UK, we saw 67 to 97%, whereas for Brazil, it was 41 to 76%. So you can see here that understanding the confidence intervals gives us a better estimate. You have two separate trials, and having two separate trials gives us a sense of where the true efficacy might lie, which is somewhere in the middle would be a better estimate. So we want to get a confidence interval for our values. So if some values are our mean, and our formula for getting a confidence interval is t, our t distribution, which is a function of the sample size by the standard error. So if we have n equals 6 with a mean of 3.5, a standard deviation of about 1.9, we can get our standard error from this formula. So 1.86 over the square root of 6, so it's around 1-ish. Our degrees of freedom is n minus 1, so that's 5. Our t-stat is 1.476 then. So then we get a confidence interval of about 3.5 plus or minus these formulas. So that's 2.4 to 4.6 for our 80% confidence interval. For our 90% confidence interval, our t distribution is at a different point. So 1.46 might be here and here, plus or minus 2.57 might be out here and out here. So that gives us our wider 90% confidence interval compared to our 80% confidence interval. Hence, we have this value for t. We have the same standard error listed here. So that gives us a wider value of 1.5 about 5.5. So it's a wider confidence interval for this 95% and a narrower one for 80%. To look at our prediction interval, it has a similar formula. So you have t by the mean squared error and a slightly different formula inside here. So what we can do if you compare that to the prediction confidence interval is that there's slightly more terms there, which means that we have a larger value in essence for our prediction interval range. And that makes sense because our goal here, distinct from confidence intervals, we're looking at population mean, we're looking at a conditional mean, whereas prediction intervals, we're looking at the next data point. So that depends on the conditional mean and the conditional variance. So we can consider in this plot here, what is the prediction interval in this plot here? So we have our data points in, let's say, black circles. What's the least squares regression fit and what's the 95% confidence interval? So you can see here we have this plot here. So what big is the prediction interval, the confidence interval, and the actual fitted line? And we'll look at that in class. We can also consider what difference does n equals 50 or n equals 5 make for a prediction interval and confidence interval. And we'll see that those ranges will change markedly between those two different items. We can also do the same for our confidence interval for our slope as well, which is its own distinct formula coming from the mean squared error and the sum squared for x. So this can be used to estimate our confidence interval for beta again, which will have some sort of an interval. To do this in R, which we'll talk about in the demonstration videos, if our model is y is equal to beta by x plus a, we can use this function confint to give us our confidence interval, which makes these calculations mentioned before a lot more simple to do. So by doing that, what we'll get is an estimate like this of our 95% confidence interval. You see here for the intercept is a very wide range, and the same for height. We're going from minus 3.8 to 6.6, so that's very, very wide if we have a small sample size. So you see there for our estimate of 45.4 and 1.4 that we have wide ranges there for the impact of height for a sample size of 50, because the effect of height on weight in that case is quite small. So that completes our video. Please see the demonstration videos for more illustrations of how to actually run these things in R with lots and lots of examples.